In this lesson we are going to learn about series AC circuits. Okay, so we are going to see what happens when my different elements are connected in series across a AC voltage. Okay, we are going to try to understand what is the current that flows when I have, let's say, a resistor and let's say a inductor connected in series with a AC voltage. Okay, so let's first analyze this situation, which is a RL series circuit. Okay, we are assuming this resistor has resistance of R ohms and this inductor has inductance of L Henry. Okay, now if you remember, when we were analyzing pure capacitive or pure inductive circuits, we talked about impedance. Okay, so impedance is something that you can simply add when you have a series circuit. Okay, so if you have an element which is connected in series with another element, okay, let's just say this is your element 1, this is your element 2, and if your impedance for this element is, let's say, Z1 and your impedance for this element is Z2, then the net impedance is Z1 plus Z2. Okay, net impedance across these two terminals is simply Z1 plus Z2. So whenever you have resistance in a DC circuit, you can just have an analogy in AC circuit that you are going to have impedance. Okay, so series connection of resistance is R1 plus R2 plus R3, right? Similarly, series connection of impedance is Z1 plus Z2 plus Z3. Okay, now we have seen impedance offered by a inductor is equal to J omega L, right? Impedance offered by a capacitor is equal to minus J 1 upon omega C. Okay, and impedance offered by a resistor is simply equal to R. Okay, so these are your imaginary quantities, therefore these are also known as your reactance. Okay, we have seen this is my inductive reactance and this is my capacitive reactance. Okay, also referred as XL or XC. This is a real impedance. It is purely real impedance of value R. Okay, now just see our situation over here. We have a R and L which are connected in series. Okay, so we have a resistance and a inductor connected in series. The impedance of this guy is R, the impedance of this guy is J omega L. Therefore the net impedance of this circuit is what? It is simply Z is equal to R plus J omega L. Okay, let's just mark my terminals. Let's just say this is my point A and this is my point B. Okay, then basically what I've found out is my impedance across AB. Okay, now if you want to find out what is the current flowing through AB, then that would be simply voltage across AB upon impedance across AB, right? Let's just say my voltage over here is V is equal to Vm sine omega t. Okay, let's get rid of this thing. My voltage is equal to Vm upon sine omega t. So essentially this voltage can be expressed as Vm angle minus 90, right? Sine omega t can be written as cos of omega t minus 90. Therefore in phasor form this is Vm angle minus 90. Okay, and your current through this circuit, if this is your I, is given by VAB upon ZAB. Okay, which is simply going to be what? Your current is going to be Vm angle minus 90 upon ZAB, which is R plus J omega L.